In this video, we're going to look at deriving the unit circle. And when we first start doing this, we're going to begin by finding the trig values of angles around a circle in general. And this comes off our right triangle trig, where you think about SOHCAHTOA, where sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And you have your three reciprocal trig functions. Cosecant is the reciprocal of sine, secant's the reciprocal of cosine, and cotangent is the reciprocal of tangent. So let's look here at this first problem. We have a point that lies on the terminal side of an angle that lies in the standard position. Find the value of the six trig functions. Now, an angle lying in the standard position basically means that one point of this angle is going to be formed by a line that starts at the origin and then goes to wherever this point is located. The other side that forms this angle is going to be the x-axis. And so we have this point that's 3, 4. That's in quadrant 1, so I'll put a point that lies in quadrant 1, and it has an x value of 3 and a y value of 4. And since we want to find all the trig functions, we need to find the hypotenuse. Well, that's the hypotenuse. You'd use the Pythagorean theorem or identify this as a Pythagorean triple. So 3 squared plus 4 squared is equal to hypotenuse squared. And you wind up getting c to equal 5. And then we'd go through and we would identify what these trig functions are. Now, if you were to go through and label the sides relative to the angle, 4 is the opposite side, 3 is the adjacent, and 5 is the hypotenuse, and we'd fill in our trig ratios. So we'd end up with cosine being 3/5, sine would be 4/5, tangent opposite over adjacent would be 4/3, secant reciprocal of cosine or hypotenuse over adjacent would be 5/3, cosecant would be 5/4, and cotangent would be adjacent over opposite 3/4. Okay, now we got the same thing. This time the point here lies in quadrant 2 because I have a negative x value and a positive y value. So I drew a x and y axis. I put a point over here somewhere in quadrant 2 and drew a line from the origin up to that point, and then formed a right triangle with the x-axis. So my x value would be -5, my y value would be 12. Similar to what we just did, we want to find the length of the hypotenuse, or the distance from that point to the origin. So you can do Pythagorean's theorem. So leg squared plus leg squared is equal to hypotenuse squared. And we just solve for c. And you'd wind up getting c to equal 13. Now you go through and you look at your sides. Opposite side would be 12. Adjacent side would be -5, and 13 is the hypotenuse. And then we go through and label the values of our trig function. So cosine here would be -5/13. Sine would be +12/13. Tangent, opposite over adjacent, would be -12/5. And then we have our reciprocal function, so secant, reciprocal of cosine, so -13/5. Cosecant would be -13/12. And cotangent would be -5/12. All right, now let's accomplish the same goal, but using different kind of information. So here we're given the value of a trig function. We're told what quadrant it lies in. So we don't technically have the point, but we still have the same amount of information given to accomplish this goal, to find the values of the other trig functions. If I tell you secant is equal to -5/4 and the point lies in quadrant 3, I make a x and y axis, put a point here that lies in quadrant 3, and I draw a line that goes back to the origin. Now secant is supposed to be hypotenuse over adjacent, and so we think about our right triangles. Because the hypotenuse is you have to take leg squared plus leg squared in the square root, the hypotenuse is always going to be positive, the distance from the origin to wherever this point is located. But I could have a negative x and a negative y. So I know that the 5 in that ratio is the hypotenuse, and it's going to be positive, which means the 4 has to carry the negative sign. From here, what we would do is we need to solve for the missing leg. You go back to Pythagorean's theorem. So we'd have leg squared plus leg squared is equal to hypotenuse squared. And you'd wind up having b squared is equal to 9. Now, when I go through and I solve this, I take the square root of both sides. Remember that the square root of b squared, or any variable squared really, creates the absolute value. So the absolute value of b is equal to 3, which means you got two possible scenarios for b. b could equal positive 3, or b could equal negative 3. Well, since we're lying in quadrant 3, I have to use the negative one, not the positive one. So this leg here is negative 3. And then we'd go through and we would find the values of our trig functions. So cosine, all right, adjacent is negative 4. Opposite of the angle is negative 3. And the hypotenuse is 5. And we just fill in the remaining ratios we need. So cosine would be negative 4/5. Sine would be negative 3/5. Tangent, opposite over adjacent, negative 3 over negative 4, so positive 3/4. We already had secant. Cosecant would be negative 5/3. And cotangent would be 4/3. Okay, last one of these here. So we have the given ratio. Sine of some angle has a value of negative 5/13. It lies in quadrant 4. So I draw my x and y axes here, put a point that lies in quadrant 4, form a right triangle with the x-axis and call this point at the origin theta. Sine is opposite over hypotenuse. So I have the ratio of 5/13. One of those numbers has to be negative. The hypotenuse is never going to be negative. So I have 13 here, which means that the opposite side of that angle has to carry the negative and the negative 5. So we have this kind of information. So from here, we want to solve for the missing side. So 13 squared equals leg squared plus leg squared. So 169 is equal to a squared plus 25. And you wind up getting to 144 is equal to a squared. Now, just like the other problem, I take the square root of both sides. That's going to give me 12 is equal to the absolute value of a. And so a, that leg, could be positive 12 or a could be negative 12. I choose the value based on the quadrant. Well, we're in quadrant 4, which means you have to have a positive x value. So I'm using the positive one. Don't worry about the negative one. Then we label our side. So we have opposite side of negative 5, hypotenuse 13, adjacent side 12. We fill in our given information. So cosine would be 12/13 for its ratio of theta. Sine, we were given. Tangent would be opposite over adjacent, so negative 5/12. Secant would be hypotenuse over adjacent, 13/12. Cosecant hypotenuse over opposite, 13 over negative 5. Cotangent would be adjacent over opposite, so we'd say negative 12/5. Okay, so now we'll take our next step into the unit circle, and we're working on deriving this. We're using a triangle approach. And it starts with our special right triangles, our 30, 60, 90 triangle and our 45, 45, 90 triangle. Now, remember that the equation of the unit circle, the unit circle itself is a circle that has a center at the origin and a radius of 1 unit, which means that its equation is x squared plus y squared is equal to 1. That could come in handy based on some information we could be given down the road. But knowing that it has a radius of 1, I'm going to have the distance of all points from the center of the circle to the edge of the circle is going to be 1, which means that the hypotenuse of my special right triangles has to become 1. So what I'm going to do is I'm going to scale down the right triangle. So I need to make that 2 become a 1, so I'm going to divide all the sides by 2, and I'm going to write what their converted sides would be. So if I divide all the sides of my 30, 60, 90 triangle by 2, I get hypotenuse of 1, leg opposite of the 60 of square root of 3 over 2, leg opposite of the 30 of 1/2. We go through and we would do the same thing for the 45, 45, 90 triangle. I want the hypotenuse to be 1, so I got to divide all of my sides by the square root of 2. Now, 1 over the square root of 2, if I rationalize that, and I multiply top and bottom by the square root of 2, that becomes the square root of 2 over 2 itself. Now we're going to put these on our unit circle. So I'll start with that 45, 45, 90 triangle since it's already right there. And so we have the hypotenuse of this triangle goes from the origin to a point that lies on the edge of that circle. And now from that point, I'm going to pull a line down to my x-axis. And then we can see how the legs play. So my 45, 45, 90 triangle has opposite sides of the square root of 2 over 2, which means the location of this point at 45-degree angle of rotation counterclockwise off the x-axis has a terminal point of square root of 2 over 2 by the square root of 2 over 2. Also notice the other 2 points at 0 degrees, because we have a radius of 1 unit, has a coordinate of 1, 0. At 90 degrees, we have a coordinate of 0, 1. Okay, now we want to start putting our 30, 60, 90 triangles in this first quadrant of the unit circle. And so I matched the colors for what we have for our scaled down 30, 60, 90 triangle. So if I had a 30-degree angle of rotation counterclockwise off the x-axis, so this angle is 30, we have the hypotenuse of this triangle is 1 because of the radius of my unit circle, which means that the side opposite of the 30-degree angle, just like in our special right triangle, is 1/2. And then the side opposite of the 60-degree angle, which would be up here, is square root of 3 over 2, which means that the coordinate x by y at the 30-degree angle of rotation would be the square root of 3 over 2, comma 1/2. And then for our 60-degree angle of rotation, we kind of have to rotate that triangle a little bit. We still have a hypotenuse of 1 unit. We have this angle of 60 degrees. So remember, the side opposite of the 60 degrees is the square root of 3 over 2. So the side opposite here is square root of 3 over 2, which means that the side opposite of the 30-degree angle, which would be up here at the top corner, would be 1/2. In context of our coordinate plane, the 1/2 is x. The square root of 3 over 2 is our y. That gives us a coordinate on the unit circle at 60 degrees of 1/2 by square root of 3 over 2. So what we have here is we have the first quadrant of our unit circle of degrees of rotation and terminal points. Now we're going to continue forward because we want to eventually get to the point where we have radians, and we want to have the other 3 quadrants. So as I just mentioned, we want to have radians on our unit circle. So what is a radian? Basically, a radian is, on your circle, the distance from the center to a point that lies on the edge of the circle is the radius. If I were to take the radius and start at this first point right here that I'm highlighting, and then bend it along the arc, wherever the end of one radius is, and then that creates a second endpoint to draw back to the origin, that angle that is formed is equivalent to 1 radian. So in a nutshell, what the radian does is it creates a ratio of the arc length to the radius. Now, in context of going around my entire circle, going around the entire circle is the circumference. So if I take the circumference of a circle, divide it by the radius, well, circumference is 2 pi r. Divide that by r for radius length, and we end up with 2 pi. So the distance all the way around the circle is 2 pi radians. Now, we can convert any angle measure from degrees into a radian measure, or the other way around, radians back into degrees, by using a simple formula. So radians is equal to the number of degrees multiplied by pi over 180, and degrees is equal to the number of radians times 180 over pi. So we're going to convert 4 points, and then we're going to update our unit circle. All right, so this first one, we want to convert pi over 6 radians into degrees. That means you take your radian value, so pi over 6, multiply it by 180 over pi, and see what you get. When I do that, the pi's would cancel. I have 180 divided by 6, which leaves me with 30 degrees. Now I want to convert pi over 4 radians into degrees. To do the same thing, take my radian, so pi over 4, multiply that by 180 over pi, And in doing that, the pi's would cancel. You'd have 180 divided by 4, which makes 45 degrees. Now we want to take a degree measure, convert it into radians. So you can take the number of degrees, so in this case 60, multiply it by pi over 180 degrees, and then simplify your fraction. We do that, and we wind up getting pi over 3 radians. And then lastly, let's convert 90 degrees into radians. So we take the number of degrees, multiply it by pi over 180, and we simplify. So 90 pi over 180 becomes pi over 2. And then we update our unit circle with these values. So 30 degrees is equivalent to pi over 6. So 30 degrees, pi over 6. 45 degrees is the same thing as pi over 4 radians. 60 degrees is pi over 3 radians, and then 90 degrees is pi over 2 radians. So we now have a first quadrant of our unit circle that has terminal points, degrees, and radians. Now let's talk about finding the other points that lie on the unit circle. We have two options here. We can use the equation of the unit circle to find the other coordinates based on a known x or a known y value, or we can use symmetry and reference angles, which is the preferred method, but I'm still going to show you how to use this equation of the unit circle in case we don't have one of our special angles to work with, and we still wanted to know where the point would fall. So here in this first problem, we want to find all coordinates on the unit circle that have an x value of 0. Well, we'd use our equation of the unit circle, x squared plus y squared is equal to 1. Put in 0 for x. We'd solve for y. So 0 squared plus y squared is equal to 1. So we have y squared is equal to 1. Solve for y. We take the square root of both sides. The square root of y squared is the absolute value of y. So I got the absolute value of y is equal to 1, which gives me two possible values for y. Y could be positive or negative 1. We're trying to find coordinates that have an x value of 0, so one coordinate would be 0, 1. The other coordinate would be 0, negative 1. I do the same thing here on this next one, so I want to find all coordinates that have a y value of negative square root of 3 over 2. So I'd put in negative square root of 3 over 2 where the y is in the equation of my unit circle. So x squared plus y squared is equal to 1. You square that radical, we'd have x squared plus 3/4 is equal to 1. Subtract the 3/4, we have x squared is equal to 1 over 4. Take the square root of both sides. The square root of x squared is the absolute value of x. The square root of 1/4 makes 1/2. So we have two possible values for x. X could be positive or negative 1/2. So we have to put that back into a coordinate. So remember, the y value of this or these coordinates was the negative square root of 3 over 2. And the x values are either positive 1/2 or negative 1/2. All right, here, finding all coordinates on the unit circle that have an x value of negative 1 over the square root of 2. So we're going to put negative 1 over the square root of 2 in for the x in the equation of our unit circle. We'll go solve for the y values. Well, negative 1 over the square root of 2 being squared makes 1/2. So 1/2 plus y squared is equal to 1. We'd subtract. We end up having y squared is equal to 1/2. Take the square root of both sides. Square root of y squared is the absolute value of y. The square root of 1/2 is the same thing as 1 over the square root of 2. So y could be two possible numbers, positive or negative, 1 over the square root of 2, which I could rationalize that, and that makes the square root of 2 over 2, but I'm not because of what I started with. So these coordinates have x values of negative 1 over the square root of 2. The y values that go with these coordinates is positive 1 over the square root of 2 and or negative 1 over the square root of 2. And lastly here, we want to find all coordinates on the unit circle that have a y value of negative 1/2. So I put in negative 1/2 for the y. And we start solving for x. So negative 1/2 squared makes positive 1/4. Isolate the x squared. We got x squared is equal to 3 over 4. We take the square root of both sides. the square root of x squared is the absolute value of x. The square root of 3/4 is the square root of 3 over the square root of 4 to the square root of 3/2. And then we have two possible values for x because that absolute value, x could be positive or negative, square root of 3 over 2. So our coordinates here that would have a y value of negative 1/2 that lies on the unit circle would be positive square root 3 over 2 or negative square root 3 over 2. So I mentioned just a minute ago that there was a second option to deriving the other three quadrants of the unit circle was using symmetry and the reference angles. Now when we made our quadrant 1 points, so our 30-degree point, our 45-degree point, our 60-degree point, and their radian values and their terminal points, quadrant 1 is my reference quadrant. And so I want to use that quadrant to make quadrants 2, 3, and 4. Well, keep this in mind, is that the circle has an infinite number of lines of symmetry, but in context of coordinates, I could take this quadrant, I could reflect it over the y-axis, puts me in quadrant 2, which means that take the x values and make them negative, keep the y values the same. So I can just copy all of those terminal points over there on the right-hand side, just make the x value negative. Once I do that, I can then take my whole top half of my circle and reflect it over the x-axis, which means that keep all the x numbers the same, but make all the y numbers negative. And so I just copy those points. Now, I could do that. The question is, well, what about the angles? And so we're going to start here with degree angles. My x-axis here, I have a starting ending point of 0 and 360 degrees because it's 360 degrees to go all the way around the circle, which means that to go halfway around the circle here is 180 degrees. We know that we have our angles, all of our angles in quadrant 1. If I wanted to get the same angle in quadrant 2, what I would need to do. So I'm here in this first quadrant. I have the 45-degree angle marked here in the first quadrant. Now I'm just going to indicate that with theta. Now if I reflected this part over the y-axis into quadrant 2, the quadrant 2 angle, the overall angle from the right-hand side of the x-axis all the way over here to this point would be equal to 180 minus theta. So I basically come over here to the right-hand side of that x-axis, and then I'd have to go theta degrees backwards to get to that point. And so one way to get there would be 180 degrees minus theta. Now, if I wanted to go all the way into quadrant 3, and I wanted this, I'm still working off this reference angle here, well, I would go all the way to 180 degrees, and then the number of degrees I would have to continue going would be the number of degrees between the x-axis and that 45-degree line, which would be, is indicated by theta. So I'd have to add a theta to it, which means that to get any angle that we want in quadrant 3 based on our reference angles, we would do 180 degrees plus theta. And then in all of our points here in quadrant 4, if I want to have my reference angle of the quadrant 1 point and know what that angle would be in quadrant 4, well, we'd have to rotate in the counterclockwise direction. We'd go all the way to 360 degrees. And then once we got to 360 degrees, we'd have to back up by theta degrees. So I'd have to take away theta from 360. So 360 degrees minus whatever my reference angle was would give me that equivalent angle that lies in quadrant 4. Now if I go and we start talking about radians, it's the same process but different measures. So 0 degrees is the same thing as 0 radians. 360 degrees is the same thing as 2 pi radians. There's 2 pi radians all the way around the unit circle, which means 180 degrees would be half of that 2 pi, which makes 1 pi. Now the way that's going to change is instead of working with 180 degrees and 360 degrees, we're going to be working with pi and 2 pi. So based on our reference angle, our angles in quadrant 2 would be equal to pi minus our reference angle. Just like we had pi minus 180, or excuse me, 180 minus theta, it'd be pi minus theta. Quadrant 3, instead of being 180 plus our reference angle, it would be pi plus our reference angle. In quadrant 4, instead of being 360 minus our reference angle, it would be 2 pi minus our reference angle. And so we apply that knowledge, and then we can fully write our unit circle with the reflections and applying that reference angles, and we can get all of our points and their corresponding coordinates around our unit circle.